So good morning, everybody. Last time we stopped more or less at this point. Well, we actually stopped at the Python tutorial, but before the Python tutorial, we were stopping at this point. So we managed to review the derivation of robot kinematics and dynamics. And I want to restart from this point so that you remember vividly this equation, because this is going to be the central part for everything that's going to happen in the coming lectures. Okay, so robot dynamics is basically an equation that describes the relationship mainly between the robot's joint torques. So these are the forces that are generated by the motors. There are torques because typically we have rotational joints, and so motors generate torques, not a force, and the joint accelerations. It's a nonlinear equation because we have the mass matrix, which is a nonlinear function of the joint angles. We have this term here, which is nonlinear in the joint angles and the joint velocities. And we have also this term here, which is due to gravity, which is again nonlinear in joint angles. So probably you have already taken some classes on control, most of you at least. I guess in your if you did like industrial engineering in your bachelor, probably there is a class on control theory in your third year by Professor Severiano. So you have seen already a bit how you can control linear systems. This system here is nonlinear. So the classic control techniques coming for linear systems, they don't really apply directly to this system. So what we're going to discuss today is how do you control this specific class of nonlinear systems, which are multi-body dynamics robots. So today we're going to talk about motion control, which is typically the starting point, which is when you want to control the motion of the robot. There are also other kinds of controllers where the goal is not to control the motion, but to control the interaction between the robot and its surrounding, like force control. But we're going to discuss that another day. So when you talk about motion control, typically you have two main classes. Either you want to control the robots in joint space, so that's called joint space control, or you want to control it in Cartesian space. So you want to control the motion of the end effector of the robot, not really, you don't care about what the joints do. That's more advanced. So we start with joint space control and then we move to Cartesian space control. If we want to describe the joint space control problem in a very loose way, we can frame it in this way. Given a reference joint trajectory, qref of t. So you have a... Oh, I forgot to share the slides. Yeah. Sorry about that. They're not going to be exactly like the ones I'm projecting right now, but they're going to be pretty close. Okay, here they are. So given a reference joint trajectory, qref of t, so it's not a constant joint configuration, it's something that is moving. You want to compute the joint torques, tau, which are basically your motor commands, such that q of t is roughly equal to qref of t. So you want the motion of the robot to follow as accurately as possible the reference motion qref. And typically when we try to solve this problem, we take a couple of assumptions, which are more or less reasonable. First assumption, we can measure the state of the robot. And the state consists of both joint angles, Q, and joint velocities q dot. Does this assumption hold in practice as far as you know? Probably you don't know. So the fact that you can measure Q is accurate. Robot manipulators do have encoders at the joint, and the encoders measure exactly this quantity Q. The measurement is not like infinitely accurate because encoders like discretize the angles, but typically the discretization is so fine that it's super accurate for what you need to do. So yeah, you do measure Q. Q dot, however, you don't measure it. Typically, robots don't have velocity sensors at the joints. Of course, you could equip your robot with velocity sensors, but most robots don't have it. So what you need to do in practice when you're working on a real system is that you need to use your measurements of the giant angles to design an estimator to estimate the giant velocities. So this assumption is not really true in practice. However, designing a velocity estimator is very simple and it works very well in practice. So it's not far from being true. It's not a big deal. Second assumption we assume was that we know the system dynamics. Basically, we assume that we know this expression here. Notice that here, compared to the expression that I wrote last time, I have compressed together the gravity and the Coriolis centrifugal terms into a single term, which I'm calling H. So last time I was writing this as a CQ dot plus G. Well, this is H from now on. So you can write it, this is C of Q dot times Q dot plus G of Q. It's just more compact to use a single term. So this assumption is, let's say, holds less than the previous one because you might have a model of your robot, but typically that model is not super accurate in terms of dynamics. It can be very accurate in terms of kinematics because it's a bit easier. Kinematics is about like measuring angles and distances, so it's quite easy to get good accuracies there. Dynamics, it's about measuring masses, centers of mass, and inertia matrices. It's a bit trickier to get accurate measurements of that. And actually, the most important thing that we are not modeling here, but that plays a big role in robot dynamics is joint friction. Of course, we could add a term, like in here, we could add a term which is, I don't know, dq dot, which accounts for viscous friction. You can estimate viscous friction on the robot, it's not a problem. The problem is that typically robots have a lot of discontinuous friction. So the friction that only starts applying when you go from zero velocity to some velocity. That's the so-called Coulomb friction. I don't know if you've ever studied this in some other classes. And that friction effects are quite nasty because they are discontinuous. So you go from having no friction to having some friction when you start moving. And so it's pretty difficult to deal with them. So we are neglecting them at this point. But that's a bigger problem, I would say, of these assumptions that we assume we know the dynamics. We do know it, but there is a friction which is hard to identify, to model, and even harder to compensate when you're doing control. But for the moment, we're going to neglect that. and we're gonna move on with our design of joint space control. So there are different ways in which you can design a joint space controller, depending on which robot you want to control, the accuracy you want to achieve. Yeah, those are mainly the two factors. Let's start from the simplest controller ever. Probably you have already encountered this kind of controller in some other classes. It's a PID control. Who has already seen PID control? Okay, most of you. So PID control is a model-free control technique. So you don't have any knowledge on the model of the robot. So basically we are dropping the second assumption. We don't need to know the system dynamics. And your controller is simply composed of three terms. You have a proportional term, an integral term, and a derivative term. And that's where the name comes from, PID, proportional, integral, derivative. So the only thing you need to do is to measure your state. So you need to measure Q and Q dot. Then you compute the error between the reference joint angle and the measured joint angle. That gives you the error E. You compute the velocity error, which is the difference between the reference joint velocities and the measured or estimated joint velocities. And you compute also the integral of the error. So every time you compute the error, you basically sum it up to the quantity you had before. And then you have these three parameters of the controller, which are called the PID gains. So Kp is the proportional gain, Kd is the derivative gain, and Ki is the integral gain. Notice these gains are matrices. They're not vectors, they're not scalar, they're matrices. Because they're multiplying a vector, the error is a vector, and they need to produce a vector because the joint torques are a vector. So the gain matrices need to be positive definite, and most of the time actually they are diagonal matrices, which means that each joint is controlled independently of the other joints. So the torque that you apply at your elbow joint only depends on the error that you see at the elbow joint. It's independent of what's happening at the other joints. Okay. So that's why this is called like a decoupled joint controller, because each joint is controlled in a decoupled way with respect to the others, which doesn't make too much sense because we know that the dynamics is actually coupling all the joints. So the motions that you have at one joint depends also on the torque that you generate at the other joints. There is coupling between all the joints. They're not independent because they are part of the same body. So here we are actually simplifying a lot things with this controller. This simplification is an advantage in terms of implementing this controller on a real robot, of course, because it makes your life easier. But it comes with the price that you don't have any guarantee that this is going to work. So theoretically speaking, there is no guarantee that you're going to be able to really track the desired trajectory with any level of accuracy, which makes very much sense to me because you're not using any model information basically. So here the performance of the controller is entirely dependent on the three gains, Kp, Kd, Ki. So it depends on how you are good at tuning those gains. Okay, so it takes some experience to make this work. It's not too difficult. I've done it several times. And it does work pretty decently in practice, but again, it depends on which robot you're controlling, which motion you want to generate, what accuracy level you want to reach. But it can work in many situations, and it's quite common in industrial robots. Theoretically speaking, the only thing we can say is that if the reference joint trajectory stops, so you want to reach a fixed configuration, then we can have local convergence, which means that if you start sufficiently close from the configuration that you want to reach, this controller is guaranteed to reach that configuration eventually. It's not a great result. We would like something better, but it's better than nothing. And another thing we can say is that if the system reaches a steady state, so if it stops eventually, then it can only stop if you have reached QREF. How can we say that? That is actually very simple to show, because if we write the dynamics of the system here, so mq double dot plus cq dot plus g equal tau, and then we know that tau is going to be equal to this controller. So tau is equal to kp times my tracking error plus kd times my velocity error plus ki times the integral of the error. Then if I assume that I have reached steady state, it means that q dot and q double dot are 0. So this term becomes 0, this term becomes 0, this term becomes 0. And the only terms that are left are g equal kp times the error plus ki times the integral of the error. So my closed loop dynamics simplify to just these three terms. And now what I can do is that I can take the time derivative of both sides. So if these two sides are equal, then also their derivatives with respect to time must be equal. But since I'm at steady state, nothing is moving. So the time derivative of g is going to be 0 because it's constant. Also, the time derivative of the error must be 0 because q dot is 0. So also this term here is 0. And the time derivative of the integral of the error, well, the derivative is simply the inverse operation of the integral. So if I take the derivative of an integral, I get the quantity I'm integrating. So the time derivative of this is simply ki times the error. And what I get is basically 0 equal ki times the error. And since ki is positive, the only way this is possible is if the error is 0. So basically, I've shown that if steady state is reached, then the error must be 0, which means q equal qref. Again, it's not a great result because I cannot prove that a steady state will be reached. So it's possible that the robot will never reach a steady state. It will keep moving forever. But in case it stops, well, in that case, it's going to stop in the right configuration. Any question on this? Okay, let's move on to a slightly better control law, which is PD plus gravity compensation. So here we are using some model information, but not all of it. So the controller is the following one: tau equal kp times the error plus kd times the derivative of the error plus gravity terms. So here we are replacing the integral term that we had before in the PID with the gravity compensation. So we are only using that part of the model. We are not using the Coriolis centrifugal terms. We are not using the mass matrix. We are just compensating for gravity because actually gravity tends to be the most important part of the model to compensate for. So in practice, what are the advantages of this? Well, you get better tracking than with a PID. It's also a bit easier to tune because now you only have 2 gains to tune instead of 3. So it's easier. And theoretically speaking, we get global asymptotic stability for a fixed configuration to reach. I'm gonna skip the proof, just telling you that you can prove this by using Lyapunov theory. If you're interested, actually the proof is very nice to look at, in my opinion. You can find it in the references that are in this shared spreadsheet. It's a very well-known proof for classic robotic theory. So I'm not going to show you the proof. I'm just going to tell you that you can prove that. So global asymptotic stability, what does it mean in practice? It means that it doesn't matter your starting configuration. You're always going to reach the reference QRF asymptotically. So like in infinite time. And it's not only about convergence, so it's not only about what's going to happen in the long run, it's also about stability. So if you start close, you're going to remain close. You're not going to like deviate going far away before reaching it. You're going to stay close. That's what stability means in an intuitive sense. We can also do the steady state analysis like we did before, to show that basically if we reach a steady state, then it must be that the error is 0. Here it's even simpler. You just write the dynamics of the robot on this side, the control law on this other side. You know that these 2 terms must be equal. If you're at steady state, then everything that depends on velocities, accelerations, is 0, so you can remove these terms. Then you have gravity on both sides, so again the 2 terms cancel out, and you're left with Kp times the error equal to 0. Since Kp is positive definite by assumption, then the only way this is possible is if the error is 0. Okay. But in this case, we actually have a property which is much stronger than simply if steady state is reached, we are at E equals 0. The property we have here is global asymptotic stability. So we know this is going to work, period. So this is much, much stronger than what we had before with the PID. And even this control law is very common in industrial robots. Okay, so this is used a lot in practice. Because with just a bit of extra modeling, you can improve a lot the performance of the robots. Especially if your robot is heavy, which most industrial robots are, then gravity is going to be a big part of the torque that you need to generate for moving it around, because the masses are high, and so the gravity torque is going to be large. We can do even better if we want to achieve like higher performance. And to do better, we need to use the whole model of the robot. And if we do that, we get a controller which is called, well, it has many different names. The one I use is inverse dynamics control, but it's also known as feedback linearization or computed torque control. Actually, feedback linearization is more like a term coming from control theory, and it's a more general technique for any kind of nonlinear system, for like many kinds of nonlinear systems. Computed torque instead comes from the robotics community, and it's like a more old-fashioned terminology. People nowadays call this more like inverse dynamics control. Why is it called inverse dynamics control? Well, because it relies on this expression here, which is the inverse dynamics of the robot. If you remember, I defined inverse dynamics last time. It's the problem where you know the accelerations, the velocities, and the positions, and you want to compute the torques that correspond to those. And that's exactly what we are doing here. So in this controller, you're going to use the acceleration of the reference joint motion, q double dot ref. You're going to sum to that two feedback terms, one proportional to the error, kpe, one proportional to the derivative of the error, kd times e dot. And then you're going to take this quantity here, which is basically an acceleration. You're going to scale it times the mass matrix of the robot, and you're going to sum to that all the nonlinear effects. So inside H, if you remember, there is the gravity terms, Coriolis, and centrifugal terms. So to implement this controller, contrary to what we had before, you need to know the complete dynamic model of the robot. Otherwise, you cannot do it. In this case, it's actually very simple to show that this is going to work. You can write down the dynamics on the left side and the control law on the right side of the equality. And since you have all the nonlinear terms which are compensated by the controller, the two H cancel out. You have the mass matrix on both sides. If you remember last time, I told you that the mass matrix is symmetric, positive definite. Positive definite and symmetric. So if a matrix is positive definite, it means that it is invertible. So we can actually remove the mass matrix on both sides because we can just multiply times its inverse. And what we are left with is the following expression. So the joint accelerations are going to be equal to the reference accelerations plus the feedback terms. This dynamics here is linear. There is no nonlinearity here. Everything is linear, which means we can rely on linear control theory to analyze its behavior. So if I move everything on one side, what I get is the following expression in terms of the tracking error E. So I get E double dot plus KD E dot plus KP E. So it's a linear dynamical system of order 2 because I get derivatives up to the second one. I can rewrite this as a first order linear dynamical system by defining a new state vector, which is Y, which contains E and E dot. That's a classic trick when you're working with a linear dynamical system. So if Y contains E and E dot, then the time derivative of Y, which is Y dot, is going to contain E dot and E double dot. And so now I can write the dynamics in terms of Y. And the dynamics takes the following form, Y dot, which is nothing more than E dot and E double dot, is equal to a linear expression of Y. So the linear expression is defined by this matrix A. The first row of A is simply 0 identity matrix, because I'm simply multiplying 0 times E, so I get 0, plus the identity matrix times E dot, which gives me E dot. The bottom row instead contains minus kp and minus kg. And if you do the math, do the multiplication between this row and this vector, you basically see that you're recovering exactly this expression here. So I'm simply rewriting the same equation in another form so that it's a first order system instead of a second order system, but I didn't change anything in terms of content of the equation. And the reason why I'm writing it as a first order system is that I can use then results for that are holding for first order linear systems. So if you have taken some class on linear control theory, working with state space models like this one, you will know that a system of this kind is stable if and only if you take the eigenvalues of this matrix, you look at the real part of those eigenvalues. If that real part is negative, you have stability, global asymptotic stability. And in this specific case, this matrix is going to have eigenvalues with negative real parts if the gain matrices are positive definite, which was our assumption in the first place. So basically, this controller gives us global asymptotic stability, assuming that we have positive definite gains. So easy. So here in theory, you don't need to be good at tuning it. It's going to work, period. Just use positive values for Kp and Kg, and you're going to be good. It's going to be globally asymptotically stable. Then globally asymptotically stable doesn't mean it has good performance. Okay, so you will need to be a bit good at tuning it, but it should at least be stable no matter how you tune it. So in terms of like theoretical guarantees, this is the best we have seen so far. However, in practice, this is much less used than the other two control laws we have seen before. Can you guess why? Yeah, you need to know much better the model of the robot. So you need to know the mass matrix, you need to know the Coriolis and centrifugal terms. These are all quantities that depend on the inertia tensors of the links of the robot, which is a bit tricky to identify. Whereas gravity only depends on the masses of the links, which typically you know quite well, and the centers of mass of the links, which again are easier to identify than the inertia tensors. Okay, so remember this controller here. Look at it, because now I'm going to show you a variation of this control law, which is very common in practice, which is the following one. It looks almost the same as the previous one. Did you spot the difference? Yeah, basically. So in this case, the mass matrix only multiplies q double dot ref, whereas in this case, the mass matrix multiplies q double dot ref and the PD terms. So basically, you're taking these two terms here and you're moving them out of the multiplication with the mass matrix. And you get this variation of inverse dynamics control, which is called with the same name, inverse dynamics control. They don't have two different names. That's why I'm calling it a variance of inverse dynamics. So you're not changing much in terms of assumptions and need to know the model. You still need to know the mass matrix and all the dynamics. It just happens that this one in practice can work better in many cases. The reason why is theoretically unclear, even though I have some guesses, but there is no theory supporting that that explanation. So just know that in practice this may work better. And it's quite easy also to analyze the closed loop behavior of the system under this control law. It's a bit more difficult than with the previous one, but not much. So you write down the dynamics as usual on the left-hand side, the control law on the right-hand side. H, you have it on both sides, so it cancels out. Then you can multiply both sides times M inverse, so the inverse of the mass matrix. So M disappears here and here, but you have M inverse appearing here in front of the two PD terms. And now you can basically define new gain matrices, Kp bar and Kd bar. You define them simply as the mass matrix inverse times Kp and the mass matrix inverse times Kd. And here, to show that this is also a stable system, you need to know that here you're multiplying two positive definite matrices because M is positive definite. Also, its inverse is positive definite. Kp and Kd are positive definite by definition, by assumption, sorry. In general, when you multiply two positive definite matrices, the result might not be positive definite. So this doesn't hold in general. The reason why I'm saying that this product is positive definite is because we took the assumption that Kp and Kd are not only positive definite, but are also diagonal. Symmetric is not enough. You need them to be diagonal for these two poles. So if these new gain matrices Kp and Kd bar are indeed positive definite, then basically the expression that you get here is kind of the same of what you had before. So it's again a linear dynamical system, and it's going to be stable because of the same reasoning we did before. Any question? Okay. So this was the last control law that I had to show you for joint space control. Before moving on to Cartesian space control, want to clarify these different ways of controlling robot manipulators are part of what's called like classical robot control methods. So these are control methods that have been developed a long time ago, like the 70s, the 80s, like classic control methods. I'm not showing you this because this is going to be the main topic of this course, but I need you to know a little bit the basics so that you can appreciate the difference between these like classic old school control methods with respect to the more modern optimization based control method that I'm going to explain you later. Okay, so you can see the difference, and we can see some comparison in simulation between what you can do with these methods and what you can do with the optimization based modern control method later on. Okay, that's also why I'm going so fast in explaining this, because this is not going to be the main focus of this course. And actually, probably if you have taken another class on like foundation or introduction to robotics, you may have already seen some of that, if not all of those. Who has already seen some of these control methods? Yeah, almost all of you. Okay, so this was just a review of what you had already seen. Let's now move on to a more complex control problem, which is controlling robots in Cartesian space. What's the difference between joint space and Cartesian space? Well, now the assumption is that we are given a reference trajectory for the end effector of the robot. So we don't know how the joints need to move. We don't care, actually. We only care about what the end effector is going to do. This is actually much more useful in practice because typically that's what you care about, the motion of the end effector. And you want, again, to compute the joint torques, which are your motor commands, your control inputs, such that the behavior of the end effector, the trajectory of the end effector closely tracks the reference trajectory. So to simplify our lives, I'm going to assume from now on that when I say the end effector, I mean the position of the end effector, not the position and the orientation of the end effector, even though in practice, very often you also care about the orientation of the end effector, not only the position. So you care about positions, which is 3D, and orientation, which adds another 3 degrees of freedom to your so-called task space. But if we introduce orientation, then we need to deal with the whole problem of working with quaternions and the fact that the derivative of the quaternion is not the angular velocity. And so things become a bit more convoluted. Not too much, but they complexifies the notation and all the discussion. So to make sure that things are simple and you can understand them, for the moment, we're going to stick only to controlling the position of the end effector. Just know that it doesn't take much to generalize what I'm telling you to controlling also the orientation. It's just a little bit of extra complexity. So a first idea that I want to discuss so that we can then rule it out is that actually, even if your goal is to control the end effector of the robot, you don't need to have a controller working directly in Cartesian space. Because what you could say is that, well, I have my reference trajectory for the end effector. I have this to begin with. So I can do all the pre-computation that I want with this trajectory. And in particular, what I could do is that I could compute a corresponding reference trajectory in joint space such that following this reference in joint space allows the robot to follow the reference that I was given in Cartesian space. Okay, so I can compute this mapping. Do you know what problem I have to solve to compute this mapping? What's the name of this problem? It's a very common robotics problem. Yeah, it's typically called inverse kinematics. I prefer to call it inverse geometry, but that's just me and a few other people in the world. Which is not an easy problem, but it's not super difficult either. And especially you can solve it before controlling the robot. So you can take all the time that you want to solve it. But it's a nonlinear optimization problem, basically, that you're solving. Unless you have an analytical solution that is specific for the robots you're controlling. But in general, you don't have an analytical solution. So you need to rely on numerical methods for solving this problem. So it can take a while. So you could do that. And then basically you have a reference in joint space, and you can go back and apply one of these techniques for joint space control. And I guess that in practice, many people do that in industrial settings. What's the limitation of doing that? Can you foresee any limitation? Imagine that your robot needs to pick up objects that are coming on a conveyor belt, like in the videos I was showing you in the first lecture, you remember? So you had these objects coming on the conveyor belt and the robot needs to pick them and move them somewhere else. Were the objects exactly all in the same position? No. Was there a way to anticipate what the position would be? No. So the robot would discover the position of the object only when the object would arrive. Do you see where I'm going with that? No. Here the assumption is that you know the reference trajectory beforehand and you can do this computation offline, taking as much time as you need. But in practice, in many practical cases, that's not true. You only know the trajectory for the end effector when it's time to start moving. And so you cannot do any pre-computation. You cannot do that offline because you only know xref when you see the object. And when you see the objects, you need to hurry up and pick it up because otherwise the conveyor belt is going to move it forward and then it's out of your workspace and you cannot reach it anymore. Okay. So in many cases, the robot doesn't know in advance what kind of motion it has to do. I mean, roughly, yeah, it has to go on the conveyor belt and move to the table on the other side, but you don't know exactly where it's going to go. Okay, so you cannot do this pre-computation offline. So if you're in one of these situations, this idea is trash, and you need to have a Cartesian space controller. So let's see how you can do Cartesian space control. So one very famous, well-known way of doing Cartesian space control is the so-called operational space control. This is a method that was proposed in the 80s. It's pretty old, as old as I am. And it's based on this idea that we can take the dynamics of a system and we can project it in the space of the end effector, the so-called operational space. So we can basically do a bit of math and get an expression that looks a lot like this one, so which is the standard dynamics of a robot, which is in joint space, but it's going to be expressed in quantities in Cartesian space. And then once we have that dynamics in Cartesian space, we can design a Cartesian space controller in the same way we have designed a joint space controller before. So let me show you how you do this conversion from joint space dynamics to operational space dynamics. When I say operational space dynamics or operational space in general, you can think of it as Cartesian space for the moment. Okay, I'm going to use these two words to mean the same thing. So we write down the dynamics of the robot in joint space. So mq double dot plus h equal to tau. And then I'm going to pre-multiply on the left both sides of the equation times j m inverse. So m inverse is, of course, the inverse of the mass matrix, which we know exists because the mass matrix is positive definite. J, we have already seen this. Do you remember? What's J? The Jacobian matrix, yeah. So I'm going to call it the end effector Jacobian to be accurate. And you can define J as the derivative of the forward geometry function with respect to the joint angles. So if you do this multiplication on both sides, what you get is jq dot plus jm inverse h equal jm inverse tau. Nothing surprising here. The only thing that happened is that m inverse times m equal the identity, so I removed it. Now I need to work on this term, jq double dot. The way I'm going to do it is by exploiting the relationship that there is between the velocities in joint space and the velocities in Cartesian space, which is defined by the Jacobian. So we have already seen that the velocity of the end effector can be computed as j times q dot. I've shown you this last time. So if now I want to move from velocities to accelerations, I can simply differentiate the two sides of this equation. So the derivative of x dot is going to be x double dot. So if you differentiate the velocities, you get the accelerations. On these sides, you have a product between j and q dot. So when you differentiate a product, you remember, hopefully, from your analysis classes, the derivative of a product is the derivative of the first term times the second term plus the first term times the derivative of the second term. So that's exactly the rule I'm applying it. So I get j q double dot plus j dot q dot. So maybe you haven't seen that rule being applied to matrix vector multiplications, because typically in analysis you apply that to scalar quantities, but it applies exactly in the same way when you have vectors and matrices. So this is one of those beautiful cases where the rules you learn for scalars still apply to vectors and matrices. It's not always like that. In this case, it does. So now we have an expression that is telling me the relationship between the accelerations in joint space and in Cartesian space. And I can use this expression here because I have jq double dot here. And from that expression, I know that jq double dot is actually x double dot minus j dot q dot. Is that clear? The reason why I did that is because my objective is to move from joint space to Cartesian space. And now here, I managed basically to get rid of the joint space accelerations in exchange for the Cartesian space acceleration. So I'm moving towards my objective. Now I'm going to do something weird because it's a bit hard to justify. I'm going to multiply both sides of this equation times a new matrix, which is called lambda, which is defined here. Lambda is a so-called operational space mass matrix. So this is going to be acting as the mass matrix in joint space, but for the Cartesian space. And the way this matrix is defined is in the following way. So it's J times M inverse times J transpose, everything inverted. It's a bit convoluted. But that's basically the equivalent of the mass matrix in Cartesian space. If you do this multiplication, then you get this expression here. And we already see that here we have something that is very similar to what we had in joint space. So we have the product between the accelerations and the mass matrix. Good. The second term, I'm going to call it mu. and it's going to act basically as the term h in the original expression. And on the right hand side of the equation, I have this lambda j and inverse tau, which is the only part that is not yet in Cartesian space, because tau is still a joint space quantity. So if I want also my control inputs to be expressed in Cartesian space, what I can do is that I can assume that tau is equal to J transpose times a new like virtual control input, which I'm calling FC. So it's like a virtual force that I apply at the end effector. And the reason why I'm doing that is that it allows me to simplify also the equation, because if I substitute tau in there, what I get pre-multiplying FC is lambda times J and inverse J transpose. But lambda is exactly the inverse of J and inverse J transpose by definition. So I'm getting a matrix times its inverse. And we know that if you multiply a matrix times its inverse, you get the identity, so you can remove it. And so what I'm left with after that substitution is the following expression. So lambda x double dot plus mu equal FC. That is the operational space dynamics I wanted to reach. And you can see the structure is exactly the same as the original joint space dynamics. We have the mass matrix M, which becomes lambda, the joint accelerations Q double dot, which becomes and the effector acceleration X double dot. We have the nonlinear terms in joint space, which become nonlinear terms in Cartesian space. And then we had the joint torques, which become this like virtual and effector force, which is our new control input for the system. Now that I have the dynamics expressed in Cartesian space, it's going to be pretty straightforward to design the controller, because I can do the controller exactly in the same way we saw for joint space. In particular, I'm going to replicate what we did with the inverse dynamics control in joint space. I'm going to do it here now for operational space. So remember that expression, because I'm going to use that in the next slide. So I'm going to choose my new control input, FC, in the following way. The operational space mass matrix lambda times the reference acceleration plus PD feedback terms plus the nonlinear effects mu in operational space. That's exactly the same thing that we did when we were doing inverse dynamics control in joint space. So there's no new information here. To simplify a bit the notation in the following, I'm gonna express this whole quantity, which is the reference acceleration plus the PD feedback, as x double dot d. That's basically my desired end effector acceleration. And now that I have my virtual control input defined, I have to map it back to my real control inputs, which are the joint torques. But that's very simple, because I know that I assumed the joint torques to be equal to J transpose times this new virtual inputs FC. So I'm simply going to take this quantity and multiply it times J transpose to get the joint torques. So tau equal J transpose FC, then FC is equal to this quantity here. So I substitute and I get J transpose times lambda x double dot desire plus mu. And then if I want to, I can substitute mu with its definition just to see what's inside in the end. And this is the expression that I get. Shouldn't be a surprise. If I apply this control law, I get exactly x double dot equal to x double dot desire. That's the same that we saw for the joint space inverse dynamics. So we get basically a linear dynamical system, which we can analyze exactly in the same way we did before. So the result, we know it. It's globally asymptotically stable under the assumption that you have positive definite feedback gains, which you should always have. Of course, even in this case, you need to know the complete model, the complete dynamical model of the robot. So you need to know the mass matrix, Coriolis, centrifugal forces, gravity, torques. And in this case, you need an extra bit of information, which is the Jacobian, which of course you didn't need when you were doing joint space control. But the Jacobian is actually very simple to get compared to all the other stuff. Do you foresee any potential issue with this controller? In the 80s, yes, it was very slow to calculate that, and that was the reason why people were not using it. 2025, no. You have ChatGPT running on your phone. The mass matrix is a piece of cake. But you were very close to getting the right answer because the problem is indeed with this matrix.
The invertibility of either the angle or the other reduction that we have there.
Yeah, it's one of those, not both.
I think it's the not the only one, but I'm not sure.
Yeah, M is always invertible because it's positive definite. So inverting M is not difficult. I mean, it's guaranteed to exist. The inverse that is not guaranteed to exist is the other one. Because here you're taking a matrix which is very nicely structured, so symmetric positive definite, but you're multiplying it on the left and on the right times the Jacobian matrix, which is not invertible in general, is not even square in general. It's actually going to be rectangular most of the time. So the result is going to be a square matrix, but it may be non-invertible. In particular, what's going to happen is that this matrix loses invertibility when the robot is in a singularity. So the classic example of a singularity is the elbow singularity. So if the elbow is straight, then the Jacobian loses rank. And when the Jacobian loses rank, also this matrix here loses rank because it contains the Jacobian. And so in that case, I mean, as all Cartesian, not all, but most Cartesian space control methods, when you have a singular Jacobian, it's problematic. So what you can do in practice is that instead of taking the inverse, you could take the pseudo inverse, or you could add some regularization. So you could say that instead of using lambda, you're going to use lambda bar, which you may define in this way: J M inverse J transpose plus epsilon times identity matrix inverse. So with epsilon small and positive value, typically you would set it to something like 10 to the minus 5 or 10 to the minus 4, like small positive value. That is enough to ensure that that matrix is invertible. Doesn't mean it's going to behave well when you reach singularity, but at least it's not going to crash the software. Maybe the robot is going to crash, but not the software. Okay, I think it's a good moment to stop for 10 minutes. I'll see you back here at 10:48. Before moving on with the theory, I wanted to show you a bit of results that I generated in simulation. Then we're going to generate similar results when we're going to start doing lab sessions and implementing and simulating controllers. But just to give you a bit of a flavor of the kind of things we're going to see, here I have collected a few plots testing different strategies for joint motion control that we have seen, like PD, PD plus gravity, or inverse dynamics control. So let's start with simulations that don't simulate Coulomb friction at the joints. So this is like the ideal case where your robot doesn't have any joint friction, which is never happening in reality, but it's just to see what would happen in an ideal case. So in the following examples, basically the commanded, the reference joint angles are fixed for all the joints except for one, which is this one here, where you can see that the reference trajectory is a sinusoid. Okay, all the others are fixed. So ideally, we would like to see the blue lines on top of the green lines if the controller was working well. In this case, it's working very badly, and not only for the fixed joints, but also for this one that's supposed to track this trajectory. You can see that it actually moves in a completely different way. That's because we are doing PD without even an integral term. Okay, so the robot is not able to compensate for gravity because there is no integral. The integral is the one that is compensating for the gravity after a while. Since we don't have it, there is no way this is going to converge to the, not even close to the reference trajectory. If we introduce gravity compensation, then things are much better. So we can see that at least the real trajectory is mimicking roughly the reference motion, but is not accurate. So there is a delay, there is undershoot, so it doesn't go all the way to minus 1.3, but it stops before. And even the other joints that are supposed to not move, they actually do move. Okay, so because we have coupling between the different joints, so even if you only try to move the elbow, well, also the shoulder is going to move unless you compensate for that. If instead of compensating only for gravity, we also compensate for Coriolis and centrifugal forces, in practice, nothing changes. Because Coriolis and centrifugal forces, unless you're really moving at very high speed, they don't matter that much in most robot manipulators. So you don't gain much by compensating for that quantity as well. Where you really can see a difference is when you switch from PD plus gravity to inverse dynamics control, because now you're compensating for all dynamics effect. And now you can really expect to have good tracking performance. And we can see indeed that's what's happened. So in very little time, like in 1 second, the controller is able to catch up on the reference motion, and then it tracks quite accurately the reference trajectory. And also the other joints, they do move a little, but here you should also take a look at the scale. they are very, very small. So there is motion in the other joints, but it's actually quite small. So like 0.02 radians, that's about 1 degree. So it's a very small movement for the other joints. Can you tell me why it's not perfect? Because in theory it should be perfect, right? What's the difference between this and the theory?
I didn't start with at the same starting point. I mean, the design
Yes, of course, that's not ideal, but still, the theory doesn't say that we need to start on the reference trajectory.
uncertainties.
There are no uncertainties here. The model is exactly perfect.
We are operating on discrete time instead of continuous time.
Yeah, yeah. That's a big assumption that we didn't really discuss so far. All the theory we have seen so far, and actually most of the theory we're going to see in the coming lectures, is for continuous time control, which means you assume that your controller is operating in continuous time. In practice, what you have in real robots is that the controller is operating in discrete time. So you have a loop because, well, you're working on a computer, so time is discrete and computation takes time. So you cannot update your controller every nanosecond. So you typically operate at frequencies that range between 100 and 1000 hertz. So even if the control frequency is very high, it's not infinitely high. And so there is already a source of, let's say, uncertainty, or it's an unmodeled effect. Nonetheless, this is a very good tracking performance. This is with the outer PD, so the PD which is outside the multiplication with the mass matrix. This is if you move the PD inside the multiplication, it actually improves. I mean, it's not so obvious, but here now the scale is much smaller than it was before. So before we had 0.02, now we have 0.0004, so like 100 times smaller. And the scale is that small, more or less, for all the joints. So this is like the best in terms of tracking performance. Now let's start to play a bit with the parameters of the controller and see what happens. So here we have the PD plus gravity compensation. So this is the same plot I've shown you before. And this was generated using a control frequency of a kilohertz, so 1 millisecond as control period, and a proportional gain of 30. And this is the tracking performance that you get, which is not great, but not too terrible. Now, if you increase the control period, so you make your controller slower, now you allow your controller 10 milliseconds for doing its computation and updating. And sometimes you cannot really choose that value. I mean, the control frequency may be dictated by the electronics of your robot. So maybe the electronics only allow you to update the commands at every 10 milliseconds. You cannot make it faster. Same gain, same controller, but now the behavior of the robots is very different, right? I mean, these, you can see them very clearly. These are high frequency oscillations, and they're coming from the controller, because now the controller is slower. And when the controller is slower, the same gain that was working well before now doesn't work well anymore. It's too high gain. And so what you need to do to make these oscillations disappear is that you need to decrease your gain. So I went from 30 to 10. And now the oscillations disappeared. The problem is the tracking now is worse than it was before. I mean, it was bad even before, but now it's even worse. You can see it here. I don't know if you remember, before it was like that, which was better. Still bad, but better. So that's why it's important to go fast when you're doing control, because if you have a fast controller, you can use higher gains, and higher gains mean better tracking, better performance. Okay, so going fast is not just because we like to go fast. No, I mean, it really changes the performance of your controller. Now we can make things even worse by introducing Coulomb friction. So this is a very nasty nonlinear effect that is present in any robotic system, unfortunately. And if you introduce that, of course, it's going to make the tracking even worse. You can try to fight back by increasing a bit the gain from 10 to 20, and it does improve a bit the tracking, but you can already see that even going to 20 introduces these oscillations. And on a real robot, these are terrible to witness. I mean, you see the robot really shaking like that. You can hear the noise of the motors suffering, the whole mechanical structure. You feel pain for it. So it's not something that is bearable in the long time. So take-home messages, PD plus gravity compensation. You can get decent tracking if gains are high enough, but too high gains lead to oscillations, vibrations. And the way to make the gains higher is to rely on a faster loop. So this could be fine if you manage to go really fast. Let's see the same analysis with inverse dynamics. So inverse dynamics, we started from this performance, which was very good, because here again, the scales are super small. So basically you have a perfect tracking on all joints. Here I'm using a time step of 1 millisecond, so it's pretty fast. And a gain which is pretty small, which is 10. And I have no Coulomb friction. Now, if I introduce Coulomb friction, we can already see that tracking is not that perfect anymore. We have a bit of error. It's not huge, still better than what we had with the PD plus gravity, but we have some error. How do we compensate for the error? Well, no, we don't. We just increase the Coulomb friction to see that if you increase the Coulomb friction, the error gets worse. No surprise. But we can compensate for the error by increasing the gain. So I went from a gain of 10 to a gain of 100. And now the tracking is back to being pretty good, even if I have like a quite strong Coulomb friction. You can see here this behavior of this joint. It's very typical of Coulomb friction. It's very nonlinear. See, even if the motion is sinusoidal, because of Coulomb friction, it becomes like a square wave. Because this is where the Coulomb friction is basically making the robot, the joint stick. And this is the moment where the torque generated by the motor is able to overcome the Coulomb friction. And so the joint can move again towards the target, but then it overshoots, and then it sticks again, and then it moves towards the target, then it overshoots. And so you have this kind of square wave behavior. That's very typical of Coulomb friction. Then, okay, you can make Coulomb friction even higher. You can see that you start having even here, you have this like a plateau effect. So the motion is not really a sinusoid, but it's a truncated sinusoid. It's the same effect I was describing for this joint a moment ago. And then I can try to make the controller slower. So it updates every 10 milliseconds instead of every 1 millisecond to see the effect it has. The main effect, I actually see it here. Not clear why, but probably it's the same is happening also here, but it's just less visible because of the scale. So take-home message, inverse dynamics without friction, good tracking even with low gains. We have seen it. If you have friction or actually any non-modeled effect, so having any uncertainty, you need to have higher gains to compensate for these uncertainties if you want to have good tracking. Disadvantage with respect to PD is that you need to have a good model of your robots. So more or less, these are the properties that we have discussed before, but now at least you have seen some examples of some simulations. So let's go back now to where we were before, which was here. So we derived the first controller working in Cartesian space, which is based on the operational space dynamics. And that controller is the following one. So most of the complexity of this controller is actually coming from this second term, I would say, because it contains many terms which are a bit convoluted to compute, especially this j dot q dot. It's a bit nasty to compute. So there exists a simplified version of this controller which works almost the same in practice, and it's the following one. So you can say that the joint torques are equal to J transpose lambda x double dot desired. So this term is exactly the same that we had before, but you can replace the second part of the controller, which was that very long expression, with simply a compensation of all the nonlinear effects of the joint space dynamics. So simply H. So the expression becomes much simpler, and it's quite easy to show that this is going to work well in practice. So we do the usual analysis of closed loop behavior. So we write here on the left-hand side the robot dynamics. On the right-hand side, we have our controller. So H appears on both sides, so we can remove it. And then I can multiply both sides of the expression times J M inverse. So on the left-hand side, I get J M inverse M Q double dot. M inverse times M gives me the identity, so I remove it. On the right-hand side, I get J M inverse J transpose times lambda x double dot desired. And now I should remember that the definition of lambda is exactly the inverse of this matrix. So again, it cancels out. And what I'm left with is JQ double dot equal X double dot desired. Here I have to exploit the relationship we derived before between joint space and Cartesian space accelerations. So JQ double dot, if you remember, was equal to X double dot minus J dot Q dot. And now I have to tell you that in practice, what happens is that typically this term here, J dot Q dot, is quite small because it's a term that is quadratic in the joint accelerations, even if it's not clear from this expression, but J dot is linear in the joint acceleration. So when you multiply times Q dot, you get a quadratic expression with respect to Q dot. So unless your joint accelerations are very high, this term here is going to be small. And so in practice, from this equation, we can infer that X double dot is going to be roughly equal to x double dot desired, which is what we want. So with a much simpler implementation, you get almost the same behavior. Any question before we move on? Okay. We have one last topic to cover for today, which is redundancy. So if you have already seen Cartesian space control in some other class, I guess probably you have already seen also the concept of redundancy. Who knows a bit about redundancy, at least what that is? Okay, a bit less than before, but still many. So redundancy is a property of a robot which has more degrees of freedom than it actually needs to complete the task that you're trying to achieve. So in this specific setting, where we are supposing we are controlling only the position of the end effector, the position of the end effector has 3 degrees of freedom, because that's how many variables we need to represent it. So it's a 3 degrees of freedom task. If your robot has more than 3 degrees of freedom, then your robot is redundant for that task. It means that besides doing that task, it could also do something else at the same time. And redundancy, it's at the same time a nice feature and a problem. It's a nice feature to have because it means that you have options for doing that task in many different ways, which could be useful. For instance, if besides reaching a point, you also need to avoid an obstacle. Like I can reach this point here with my hands in this way, but I can also reach it in this way by moving my elbow down. And that allows me to reach this point even if here there is an obstacle. If I had only this way, then I couldn't do it if there was an obstacle here. So redundancy is nice in general. However, it's also a problem because it can make actually your controller not work well in practice if you don't take care of it. So if we apply this controller, for instance, to a robot that is redundant with respect to the task that it has to perform, it may not work well. So the robot may behave really weirdly, can become unstable, can like diverge. Even if theoretically speaking, it's supposed to converge because we have this property. The problem is that this property only tells us about the behavior of the robot in the end effector space. It's not telling us what's happening in joint space. So you may have your robot that is behaving very well in terms of end effector motion, but in terms of joint motion, it's going crazy. And typically when it starts going crazy in joint space, and this also affects the behavior in Cartesian space. So we need to take care of redundancy if you want to have a good control performance. How can we characterize redundancy and analyze it in a mathematical way? Well, I think that a simple approach is to start from the operational space dynamics, which we just derived. So lambda x double dot plus mu equal to lambda jm inverse tau. This is the expression that we derived before replacing tau with J transpose FC, if you remember. So this expression here that is pre-multiplying tau, I'm gonna call it from now on J transpose sharp. This sharp symbol is used in the robotics literature to represent a specific kind of matrix pseudo-inverse. And the reason why is that, well, actually this matrix here is a pseudo-inverse of the matrix J transpose. Why can I say that? Well, because if you take this matrix and you multiply it on the left times J transpose, you get the identity. And that should be pretty obvious. Why? Because if you place J transpose and you add it there, it's obvious that you get the identity as a result, because you're multiplying two matrices, one of which is the inverse of the other. So this part here is the inverse of the second part if you add J transpose there. So obviously you get the identity. But the same doesn't happen if you do a multiplication on the right. So if you do J transpose times J transpose pseudo inverse, you don't get the identity. So it's an inverse only on one side, but not on the other side. And that's what basically pseudo inverses do. They work as inverses on one side, but not on the other side. So now that we have clarified what this matrix is, we can discuss the topic of redundancy. So if I have my control vector tau defined in such a way that when you multiply it times this matrix, you get 0, then it means that these joint torques are not affecting my Cartesian space acceleration. Don't know if that's clear to you. So we can rephrase the same concept in this way. Any vector tau 0 such that J transpose pseudo inverse times tau 0 is equal to 0 does not affect my Cartesian space acceleration x double dot. And I can see that mathematically because if I write down my dynamics and I add to my torques another vector tau 0, then by doing the multiplication tau 0 times this matrix, by assumption this is 0, and so this is equal to J transpose pseudo inverse tau, which means that adding tau 0 is not going to have any effect on my task space or my Cartesian space acceleration. Are we good? Okay. So there are in general torques that I can add to my control inputs that don't change anything in the behavior, in the acceleration of the end effector. However, they're going to change the behavior of the joint accelerations, because any torque affects the joint accelerations. We have no null space there. So if I want to exploit this property, what I can do is that I can compute tau 0 in such a way that this holds. And I can know that that is not going to affect at all the behavior of my end effector, but it's going to affect the behavior of my joints. And so I can compute this tau 0 in such a way that it stabilizes the motion of my joints without affecting the motion of the end effector, because the motion of the end effector, that's going to be defined by the first vector tau, which is, for instance, computed with the Cartesian space controller we just discussed. And this extra vector tau 0, it's only there for stabilizing the joint space motion. So it's taking care of redundancy. So one way I can do that is I can compute tau 0 in the following way, by pre-multiplying any vector tau 1 times this matrix, which is the identity, minus J transpose times J transpose pseudo inverse. This matrix here, maybe some of you recognize it, it's a null space projection matrix. So it's a matrix that projects any vector into the null space of another matrix. In particular, here we are projecting in the null space of this matrix here. Because if we are in the null space of a matrix, it means that when we are multiplied by that matrix, the result is 0. That's a definition of being in the null space. So these are all concepts that you probably have seen in your linear algebra classes, first year of engineering. So I guess a long time ago. It's very easy to verify that if we have tau 0 defined in this way, this property holds. We just substitute this expression. So we start from J transpose pseudo inverse times tau 0. We substitute the definition of tau 0. So we have J transpose pseudo inverse times this null space projector. So identity minus J transpose times J transpose pseudo inverse times this arbitrary vector tau 1. We do the multiplication, so J transpose pseudo inverse times identity is J transpose pseudo inverse. The second term gives me this expression here. And now the only property that I need to exploit for simplifying this is that property we had written down above. So the fact that J transpose pseudo inverse times J transpose is equal to the identity. So here, these two matrices disappear, and I'm left with J transpose pseudo inverse minus J transpose pseudo inverse, which of course is 0. So this is equal to 0 regardless of the value of tau 1. So tau 1 can be anything. I don't have any constraints on tau 1. Because the pre-multiplication times this matrix makes sure that all the parts of tau 1 that would affect the acceleration of the end effector are filtered out. You can think of this as a filter. It's filtering out all the components of the joint torques that would generate accelerations at the end effector. So now what we are left with is choosing tau 1. Because we are sure that tau 1 is not going to affect the end effector, but we need to, okay, how do we choose it? Well, we said already the objective of tau 1 is to stabilize the motion of the joints. So we can simply take a controller in joint space for choosing tau 1. So what I would suggest to take is this, like an inverse dynamics controller in joint space. And since I'm simply commanding to maintain a fixed joint angle, a fixed joint posture, qref is going to be static, which means q dot ref and q double dot ref are 0, so they don't need to appear in the control law. And I don't even need to compensate for the bias forces in joint space because that's already done here. So this is a simplified control law with respect to what we had before. So this is the way I choose tau 1. And then if I put everything together, this is the overall controller. So I have the first part, which is taking care of the end effector motion. And then I have the second part, which is taking care of the joint space stabilization. Any question on that? Okay. A little note. Here, I don't need to compensate for the bias forces, so I don't need the plus h because I have a plus h already there. So if I compensated for that in tau 1, I would compensate for it twice. This is not what I want. However, this is because I'm using here the simplified version of the operational space control. If you remember, this was a simplified version, but the non-simplified version was this one, which did compensate for h, but not in joint space. So this compensation is happening in Cartesian space. So actually what I can give it to you as an exercise. Like exercise. Prove that the above control law is almost equivalent to the following one. So that should be equivalent almost to using the original operational space control law, which was this, plus null space times a tau, I'm going to call it tau 2 just to clarify it's not the same as tau 1 above, where tau 2 is slightly different from tau 1. So if you use the standard, the complete control law for operational space, you need to add the compensation in joint space of the bias forces. And this should be equivalent to what we have above. It takes a bit of linear algebra to prove this. It shouldn't be difficult. Basically, you need to work on this plus null space times this and see how these two terms can be simplified when summed together. Okay, so you have fun with that. On Monday, I've canceled the lecture, as I already told you. So we're gonna see each other next week on Friday, same place, same time. Okay, see you next week.